Hello and welcome to 30th lecture of course on data-enabled tribological engineering from experiments to predictive model. Topic of this lecture is data-driven models for tribocorrosion prediction. This topic is still at the infancy. A lot of research is going on and we will try to summarize what is happening and what is really required for the future. Let me start with the tribocorrosion. We say it is really requiring a balance between wear and corrosion. Reason being the tribocorrosion is a combined effect of mechanical wear and corrosion, resulting from a sliding motion in corrosive environment. There are many keywords. Many relations are available in literature, but combined relation, a generic relation is still missing from literature. What's the reason? This tribocorrosion can be utilized for the benefit also. However, most of the literatures are concentrating on the detrimental effects of the tribocorrosion. What are the detrimental effects? We say there is a reinforcement, a bad effect of wear and bad effect of corrosion. That's where the tribocorrosion comes. However, there are many advantages also, but still we need to innovate, we need to come up with those advantages. While in tribocorrosion, we say material degradation, premature failure, and increased maintenance costs are the main drawbacks. There will be accelerated wear or material degradation will be at much faster pace. There will be premature failure. Life of the component will be decreased and maintenance cost is going to increase. And if we try to take some measures to minimize wear and tribocorrosion effects, then operational cost will be a primary criteria. Whatever we are doing, is it really justifiable? So often we try to go ahead the life cycle cost analysis. In that many effects are there, like what will be the acquisition cost, what is the initial cost which we really require to spend on that, what will be operational cost, what will be maintenance cost, and finally when we are disposing of that any measure which we are taking, what will be the cost of that. It can be positive, it can be negative, both. So that is also required. As I mentioned, that there are advantages. I can do a better manufacturing. I can do complete disintegration of complete equipment in shortest span of time. I may not require a lot of mechanical force for that purpose. That's also possible. And many times we use EP additives, extreme pressure additives. There is a possibility of mild corrosion, which provides a coating to us, and that can minimize the wear. So there are a number of advantages, but yet we need to explore those. So what are the advantages? We say controlled tribocorrosion processes can modify surface. We can do a surface modification. It can enhance the lubrication. It can really reduce the friction also. It can provide a gliding surface. And it can improve the material performance. But in some specific application, and a lot of research is still pending and we really require a good relations from that. So this is the future. More innovations are really required. Just for the giving some comparison, we did some experiments in our lab. We perform experiments on steel surface and phosphorus surface, and we did a 3 experiments. Total 4 set of experiments has been shown over here. You can see here is one of the MTech student who done this work, and then it showed initially there is a some wear, but when we are making this alkaline material or medium, then wear rate is reduced. In presence of mild steel, there is another material which we are trying to bring. Wear rate increased to some extent, but not to a significant extent. But now, if we bring a zinc, wear rate increases significantly. So there are many parameters. What we say, isolated workpiece in mineral water, it gives high wear rate. That's a specific wear rate is relatively low. Of course, when you are comparing with the zinc material, the wear rate is low. But when you are putting an alkaline medium, then we find this specific wear rate is extremely low. In presence of the mild steel, which is not connected in a complete environment, but there is a presence of mild steel in an alkaline media, it is increasing to some extent the wear rate, like in this case 0.0031, here it is 0.0121, 0.0135. So it's something like at least increasing 2 times. In presence of the zinc, is a workpiece connected to zinc plate in alkaline media. The presence of zinc plate considerably increases the corrosion wear rate. Reason being, there is an active surface coming into play, and then that is in presence of electrolyte. There is an accelerated wear rate. Like changing little bit of the material composition, wear rate can change significantly, and that too because of the corrosion. Again, not necessary, that is when you are using a plain water, mineral water, we are finding higher wear rate. But when we are using some sort of alkaline media, and then we are able to get a protective layer on the surface, wear rate drops significantly. Little active material, MS material is active material. In that presence of that, because of the neighborhood, wear rate increases to some extent. But in the presence of zinc, wear rate increases significantly. Now what we say, the results indicate that relative importance of wear corrosion and wear corrosion synergism. That means there is a synergy, there will be wear rate because of the exclusively force or relative sliding speed. There will be wear rate because of the corrosion, but there is a possibility strong synergy between the wear and corrosion. Now it completely depends on the electrolyte, materials and tribological conditions. So this is where we have many parameters. Tribology itself has a many parameter. Now we are trying to bring corrosion, which has also many parameter, and tribocorrosion will be naturally there will be many more parameters. When we are talking of the wear, again the wear has a number of options also. Wear can be related to erosion, can be abrasion, can be cavitation, sliding we already know, and fatigue also. These all are the wear related, and that's why we are getting many relation, many equations, but no generic equation, no generalized equation. Let me take an example of the marine wear, or we say the seawater induced corrosion. We have shown some sort of cavitation corrosion in this. This is a 200 micron scale. We are able to see the pits in this case of corrosion because of the cavitation. And then here we see the marine wear is related to the corrosion. Rate of the mechanically induced wear, electrochemical processes will be there, and of course it depends on the time of passivation. What is the meaning of that? Whenever there is a surface and there is some media, there is a possibility that corrosion may occur, but it will get passivated, it will not continuously grow. So passivation and time to passivation also matters, and sometime where it may increase continuously, sometime after increase it can decrease, and then that's where we require to understand when those things will happen. Coming to the marine wear, also related to cavitation erosion, there is a possibility of the foreign particles, a solid particle, and coming with a very high velocity. So solid particle erosion is also possible. Two body and three body abrasion is also possible. Sliding wear, particularly it can be dry or it can be lubricated. If there is a no lubricant, everything is removed, then there is a possibility of adhesion also, fatigue and fracking. So there are many options. Now when we say effectiveness of any passive or oxide surface layer, at the beginning of the course we mentioned very clearly most of the metal surfaces they are covered with oxide layer. It can be some nanometer level. Now it depends, the wear rate overall depends whether this surface coating or oxide coating is getting removed during sliding condition. If it is, then what is the recovery time and how much time that lubricant layer gets reformed, oxide layer gets reformed on that. That is the overall depending that whether there will be effectiveness of a passive oxide layer or not. One, as I mentioned here, the cavitation. Now, what is the cavitation? We say during the ship propellers, pressure fluctuation occurs, and because of the pressure fluctuation there will be growth and collapse of the cavitation bubbles. So there will, because of the air is getting trapped into the water, and there will be small bubbles that has been shown over here. You can see the pressurized zone, there are number of bubbles formed, and then when the bubbles get merged together, then there is a bubble growth. And other side, then further higher pressure, this bubble gets busted, and when the bubble gets busted, there's a possibility of high surge, high pressure, high impact, and pit formation occurs. So this is a cavitation, and it also allows a corrosion in this case. So that's why we are saying that during operation of ship propeller, pressure fluctuates, leads to the growth and collapse of the cavitation bubble near solid surface. The creation of this high velocity fluid microjet, whenever bubble is collapsing, there will be many jet because of the bubble collapse. There will be the microjet or fluid microjet, maybe roughly 100 micron in size, and moving at the velocity roughly maybe around 300 meters second. That's a high impact, and because of this water hammer, it will cause a loss of maybe formation of pits as well as a corrosion also, and material loss, corrosion will be there. To some extent, the similar phenomena has been shown over here. We say that cavitation exposed material, and there is a bubble which is coming into contact with the surface, and the high pressure, it is really it impacting the surface and fracturing the some material of the surface itself. So this is a very costly phenomena. We need to really keep a check on that. When we are doing some cost analysis, whatever measures we take, are those measures sufficient to save the cost? If not, then we may not take a measure. So towards end of this lecture, we will be discussing some financial aspect, some financial method to deal with those options also. Now we use the word erosive wear because the water comes with the particles and there is a velocity. So we are assuming there's a particle and impacting on the surface with impingement angle alpha. And already we have discussed that this kind of erosive wear can be further classified as a solid particle impingement, cavitation erosion, or there is a slurry also with the water. It's not only solid particle, slurry causes the erosion. That erosive volume can be given by VE, where there is a proportionally constant, and this is a function of impact angle, this is a function of velocity, and this is a function of particle size. So this has been given, IV has been mentioned here, and M has been shown very clearly. K is the probability of the wear particle formation, and these relations are nonlinear relations. So this is a one equation. Now coming to the equation 2, again as I say, that in literature there are many equations. So what they mention here, the wear rate is equal to number of impinging particle. So they are counting the number of particles which are impacting the surface, and what is the average particle mass, and what is the velocity of average particle, or maybe say velocity square. So basically they are looking at the force and angle also. This will decide the wear rate. Now they have written directly equal to, but in reality it will be multiplied with some constant, it will be their constant also. So there are many relation in literature, and then they are suitable, they are fine for the some situation, but not for all the situations. So we did a literature review, and this method is a Watson et al. Has been, the paper has been published in 1995, which is in a Wear journal. You can see here that the topic of the paper itself is a measuring wear corrosion synergism. So they are trying to figure out how wear assist corrosion, corrosion assist wear, and what is the synergy between these. We have picked a few the lines from a table. They have given provided table in this paper. So first one is a slurry corrosion apparatus. Second one is a pin on a ring arrangement. So they have mentioned this is a 3-body abrasion, this is a 2-body abrasion. Material which have been tested has been defined here. Particle size and type has been defined. But what is more important is the pH level, because pH for the corrosion is very important. Many times when in tribology, when we deal with the tribology, we use a word 10, total acid number. But in my view, when we are dealing with the corrosion and wear together, pH is a playing more important role compared to the only the tan number. Reason being, pH is a little more sensitive. So if I'm able to do some sort of forecasting how the pH level will change over the time, I can estimate the life of the oil itself, and based on the life of the oil we can estimate the what will be the life of the component. If we are changing the lubricant, maybe after some time, at least we can do a better forecasting. So what they try to figure out, they say the corrosion rate with and without abrasives of this corrosion thing. So they use in presence of corrosion, they found the corrosion rate in presence of abrasives and absence of the abrasive particles. In second case, they compare uh, the current which is generated. So this is what they say, the IP sliding by IP static. IP is a steady passive current. So I is current and P is a passive. So in this case, the first case, as I say, the slurry, they use electrochemical erosion corrosion apparatus. They rotated the specimen in slurry, which will also contain electrolyte, and then they change the chemical composition and pH level. You can see here the pH varying from 2.2 to 9.7. What are the recommendations? Say because of acidic nature of electrolyte. If electrolyte is acidic in nature, this synergism will intensify, where it will increase significantly. And then because of this acidic nature, media doesn't allow to form a protective film on the surface. That's why the wear rate is on higher side. So this is what they have done, and it has been tabulated in this paper. Second one, the pin on the ring arrangement apparatus, they calculate the mass. They calculate the mass after calculating the volume, which is a very good option. Reason being, earlier we say we have many times we are getting a weight directly on a weighing balance, which is to some extent may provide us some errors and some uncertainties in this case. However, in this case, they measure the width and they measure the depth. Both are very good option. If you are able to measure the width, if you are able to measure the depth, of course at every location, if you are taking some generalized one, a mean value, it may not give very accurate results. But if you are able to do a localized variation, if measure a localized variation, get a data, at least machine learning will provide a much better results. So they measure the width and depth of the one track using a profilometer. Of course, what they did a testing, they tested in a 20% sulfuric acid percentage. So it is a kind of concentrated sulfuric solution electrolyte, and then they found a synergism between wear and corrosion. They calculated very clearly that passivation current sliding to a static one, and then they found that if this current is increasing, that means energy is increasing or wear rate is increasing in this case. So that's why they say alloy with highest repassivation rate, where the alloy is forming a protective layer immediately, that will show the least wear corrosion synergism. We require a material which can repassivate immediately. That kind of material will help us. However, if we are measuring the current, we say increment of critical and steady passive current were seen as expression of increased corrosion rate due to the wear because of the wear impact of the wear. So these two papers are indicating there is a effect of pH, and if it is acidic nature, possibility of the synergy will be on a higher side. However, if the material which can repassivate immediately, this energy can be reduced. So, if we are able to provide some sort of electrolyte which is at 7, it may have a lesser problem, or maybe on a basic side, maybe 8, 7.5, it will give a very good results. Coming to the passivation side, a material which can passivate immediately, that will be preferable. They, in continuing with that table, we took last three also. In the situation, they showed the two body abrasion, three body abrasion. Again, the material tested have been shown on here. pH level in this case is a mostly alkaline, 7 to 7.7, 8 to 10, and 9 to 11.8. So that has been shown here, and then they have provided some sort of comments. In this case, they are showing very clearly the ratio of specimen hardness to abrasive hardness on will affect the total degradation, and if specimen hardness is on higher side, then the chances of wear will also reduce. And if the wear is chances reducing, the synergy also impact of synergy also will reduce. So let me explain here. We say first setup the dynamic wear corrosion, particularly in a tribo condition. They found a synergism of the wear on a corrosion, and then they measure the open circuit potential. There is always a different way to measure the corrosion and wear rate. As we have seen in previous slide, they measured the current, and the current value is increasing, that indicates a higher corrosion rate is happening. So increased wear rate of corrosion and corrosion current density increase about, in this case they observed almost 2 order of magnitude, and then from wear in presence of wear and in absence of wear. If there is a wear condition, then current density increases by 2 order of magnitude. Second experiment, jet slurry apparatus. They utilize a steel grinding ball, uh, and they try to use some sort of parameters. Again, this is also abrasive, the two body abrasion, three body abrasion, and then they compare the effect and found in a synergism. They found very clearly that if sample hardness is on higher side, total wear rate will be lower. And then in the another point comes a corrosion rate will be independent of hardness. So corrosion is not getting affected, but wear getting affected. More and more sample hardness, lesser and lesser wear, and lesser synergy also. So that's why they are saying magnitude of synergism component decrease with increasing sample hardness. The total abrasive corrosive wear increased with applied load. That means if there is a higher load, synergy will increase. And then if hardness of abrasive material, it's not a sample hardness. If the abrasive material hardness increases, energy will increase. And then pH level is going to acidic side, again synergy will increase. Even though they done experiment with the 8 to 10, then they are comparing 10 versus 8, and then they say as the pH level goes down, synergy level is going to increase. In this case, last one is a cylinder annual apparatus. They use 15% volume quartz water slurry. The slurry one, and then the degradation process of corrosion only they observed, abrasion also, so that they can compare easily, and then the total wear. And in this case, they also found the magnitude of synergism, if considerable, even in component and the corrosion component is smaller. Now here that they are finding the this pH level is a 9 to 11.8, and then they found the corrosion component is smaller, but still a synergy is there. So again this question comes, what do we go ahead? So whatever they in the second number paper and third number paper, final comments are same. Total abrasive wear of steel increase with applied load, and the increasing hardness of the abrasive material and decreasing the pH level. So the final comments are same. Only question comes that there is a variation in the results, acidic media, alkaline media, but still there is a some synergy. Can we break the synergy? Now another one, in most of the time alkaline media corrosion is not happening. In an acidic media corrosion happens significantly. If you are keeping high hardness of the samples or tribo surfaces, chances that wear rate will decrease, but this also will decrease the synergy. Even the corrosion is lesser or mid level, synergy is lesser because of the dominant role is played by the wear. The question comes, if it is, then why we are considering corrosion at all? Then we should move ahead with a complete wear. But in reality it doesn't happen. In some situation something happen, but other situation other things also happen. So this is what now we are coming back from some fun concepts of fundamentals we learn from lecture 16, that there is some sort of electropotential table, and then we use a word cathode nature, anodic nature, and we in previous slide we showed a zinc. This is the electropotential is a negative side, and because of electropotential on negative side, wear rate of the steel increases. say in this case. So this is also a wear rate in the sense is a basically deposition of the zinc material on the steel surface. So it's not a wear, but yeah, there is a some sort of surface roughness change, which in future again will increase the wear rate. So here there is a material deposition which is unwanted, we do not want, and it will lead to the create a rough surface, and rough surface will create a kind of additional abrasion. Now, in this case, another thing is that when we were on the covering the tribocorrosion, we give a lot of emphasis on the noble material. Noble material is something like a gold, platinum, silver. They don't get oxidized so easily. But here question comes, are these really good material? Here there is a problem because we say limited wear resistance due to the weak oxide layer protection. Now they are protected from a corrosion point of view, but they become a very weak inner wear. So that's why we need to rethink. Now let's take an example of titanium alloy, which has excellent corrosion resistance, but wear resistance is not really suitable for the surfaces to be used of a tribo surfaces. So this is very important to understand. Alone corrosion may not be correct, but when we are talking about the wear and corrosion, material choice also will change. So that's why we say the few material when tested at the slower is sliding speed. Another one here, now we are bringing sliding speed. Performance will be different. When the lesser sliding speed, the wear rate is lesser and possibility of reformation of oxide layer is happening. So passivation will occur. That's why we are saying the repassivate due to the tribofilm formation on the worn surface. So there is a sufficient time to reformulate the tribo surface on the worn out surface, and that is helpful. Reason being, often the tribofilm acts as a solid lubrication film, stabilize the coefficient of friction also. So here corrosion is also there, sliding is also there. What we have done, only the change in a sliding speed, and we find there is a possibility of the repassivation and overall corrosion rate will drop. Another one we mentioned, the tribocorrosion depends on the temperature. So whatever we are getting the results at the room temperature, or maybe say slightly high temperature, but that may change completely. It also depends on the pH value, where lady mentioned that if it is going this acidic nature, pH will drop, and because of the dropping the pH, overall the wear due to tribocorrosion will increase significantly. Of course, it depends also whether oxygens are present or not. In some presence of oxygen, it passive layer will form. In other cases, it will excess corrosion will occur. So it depends on the situation. Now, tribofilm can enhance the corrosion resistance by inhibiting oxygen transport also. So this is what we are mentioning. Now, one more thing comes is the carbon dioxide, and often we say we are do not have a corrosive media. But it's unfortunate we are living in an environment where there is a carbon dioxide, there is a water. So carbon dioxide and water vapor, they are very significant, even though very low percentage. But because of the Earth atmosphere, they form some sort of atmospheric corrosion or corrosive environment. So this is the water vapor, the carbon dioxide, and there are many other gases which are creating acidic nature, which are creating the corrosive environment. So that's why we need to study, whenever we are studying the wear, we need to study also the impact of the corrosion. Even though there is no intentional corrosion, but because of the environment there is a corrosive media, and we shall check it. Of course, sometimes it is a very fatal, but often it helps also. It forms some sort of oxide layer, and it kind of the barrier between the surface and other environment. Reason being, after getting formed the oxide layer, they passivate, they stop. That means a few micron layer, and after that there is a stoppage of further corrosion. So they are stopping corrosion, as well as that they are helping from a tribological point of view, because the lubrication layer, whatever the oxide layer on the surface, it acts as a lubricant layer, and it is also reducing the wear rate. So this is what I'm showing here, atmospheric corrosion. You look at the outdoor percentage, indoor percentage, or maybe say ppb. Ozone is there, hydrogen peroxide, sulfur oxide, hydrogen sulfide, nitrogen oxides, even HNO3, ammonia, HCl, Cl2. These all are the material, the gases are available in environment. So some example has been given, reason being that these are all other pollutants. Now even the sulfur oxide or a hydrogen sulfide, they can act with the moisture to form of the sulfuric acid. Of course it will be weak sulfuric acid, but it is there, or at acidic environment is there, pH level will be lesser than 7. Similarly, we will have a nitrogen oxide forming the nitric acid, which is again a corrosive nature. It will accelerate the degradation of the materials. However, severity of the corrosion, as I mentioned very clearly, corrosion may help also. It may help to reduce wear rate, it may reduce the friction also. However, the severity of corrosion will depend on the concentration. It will depend on the exposure duration. Is it for the 1 hour? Is it 10 hours? For the 100 hours? Depends on that. Depends on temperature, humidity, and material which are getting involved, or which are getting this kind of oxide layer on the surface. So these are the important aspects. Now, surface degradation caused by chloride is one of the major concern. Now, in this, because of this EP additives, earlier we were using the chloride, we have stopped. We don't use a chlorine now, it is a sulfur or phosphorus. So these are major concern as mentioned very clearly, and this is a very more common in coastal area near sea beaches and all. The or marine water, in one of the earlier slide I mentioned, this is a problem. And chloride ions can easily penetrate the protect oxide layer. So this is another problem, that really there is some oxide layer, but chloride ions can really penetrate and then create some sort of a crevices corrosion, which is a very bad or the fatal for the health of a component. That's why we say these chlorides produce a pitting or crevice corrosion, which is a kind of hidden corrosion. We say the secret kind of thing. So now here we are showing a picture, and this was shown in earlier lecture 16 also. Whenever there is a welding thing, and there will be some sort of gap available, and if there is a presence of a chloride, it can penetrate. Even though on the top surface nothing will be visible, but this the crevice will go in deeper and deeper, and finally the component will fail suddenly. And it has happened in number of bridges and number of platforms also. So these are the one of the most severe cases, and we should avoid those. Another example I'm showing here, surface degradation due to sulfuric acid. In the previous slide, I already mentioned, because of the water SO2 contained in environment, there's a possibility of the sulfuric acid. So that's why the how much sulfuric acid will impact on the surface, and that to aluminum alloy. That was experiments were done on this, not by me. It is from literature. And then they use a two different current density, one ampere per centimeter square, other one is a 7.2 ampere per centimeter square. They expose it for 30 minutes. So here the first figure, which shows sulfuric acid with a 1 ampere per centimeter square, and then we are able to see the surface is a reasonably okay, not much problem. But current density has increased from 1 to 7.2. We are able to see there is a number of fragments in these surfaces, and which will try to create some sort of crevices or gaps, and that they will create a corrosion, as well as because of that wear rate also will increase. But one more interesting thing is that initially we were thinking only the sulfuric acid as a harmful, but here in this case you can see citric acid, which is not treated as a very harmful. Even the 1 ampere per centimeter square current density, we are able to see some sort of damage to the surface also. And of course the 7.2, we find a lot of damage to the surface. So there is a need, because these all are available in environment, and then a citric acid creates this kind of problem to the material, that to aluminum material, that need to be checked properly. So that's why we say metals become weaker and flaking of the surface will occur, and then it will cause, because of this corrosion, wear will be much more, and will be significantly increased. So how do we really model whatever we explain? we say total material loss. That's we are showing volume of the mud. This is a VC corrosive wear. We subscript we are keeping a corrosive wear. In corrosive wear can be expressed in the terms of wear loss due to the pure corrosion and pure wear. That's what we are showing in absence of wear. So there's a VC, that means the loss in presence of corrosion and in absence of corrosion. Again, if there is no sliding motion, chances are there where will not happen so easily. So overall we can say that material loss due to the corrosive wear will be because of the volume loss because of the in absence of the corrosion, where volume loss in presence of corrosion, and there is some sort of synergy between these two, corrosion and because there will be interaction, there is an independent variable where independent corrosion, but there will be interaction also. So this is a synergistic effect del Vs we actually are showing. Now this del Vs can be expressed in two terms. We say this is a del Vw and del Vc. And what is a del Vw says very clearly the corrosion induced wear, while del Vc says wear induced corrosion. How do we differentiate is a little difficult because most of the time it will be synergistic effect, and then when we do experiments in lab we need to control wear and we need to control corrosion. Now here I'm just showing two figures. This experiment is been done, and this has been done in presence of zinc, so you are able to see that the deposition on the surface. So if I go ahead with the only material loss, I will not find material loss here, but there is a deposition and the zinc material is getting deposited on this surface. So how do we analyze it? We say total material loss can be given in terms of VW, VC, and then because of the wear induced corrosion and corrosion induced wear. So these two terms. However, if you want to reformulate it, we say one is related to the wear in presence of corrosion, other one is a wear in absence without corrosion and with corrosion. So WC is without corrosion and with the presence of corrosion, and this has been given reformulated in this manner: VCC is equal to VC plus del VC. WC is a VW plus del VW. Now it is easy to formulate in this manner, but we require a mathematical equation, mathematical relations. So here what we are saying, the material loss due to corrosion, that's what the VCC during corrosion wear is higher than the pure corrosion in absence of wear. Now this is another one very common thing. We say that whenever there is a wear, material will get removed, surface will get exposed to the environment, so there is a more chance of the corrosion. In other words, if there is a no wear, corrosion will be of some level, but if there is a wear, definitely corrosion will increase significantly. Reason being, whatever the passivation was happening earlier, because of wear it will be continually removed, and that is the reason the why this is a kind of reaction are happening. So in presence of wear, corrosion will increase significantly. That's what has been shown. So here we see the metal surface being activated by wear action. We say hard particle intruding and sliding. Because of the sliding motion, surfaces will be removed. So that's why that they are saying that removing the protective passive layer and increasing the internal energy. Now this energy, because of deformation, it can be blowing effect because of the abrasion, and overall the situation will be severe situation. Now coming to the equations, we say that we need to really formulate some equation for anodic corrosion current, because many authors have measured the anodic corrosion current. And how do we measure anodic corrosion currents? It can be given as a summation of these two. Anodic corrosion current can be given as a IAW. Now here two parts, one is a AR, IR. Now AR is a real area of contact, and and then the apparent area of contact is a AA. And then we are measuring two current, IR and IA. And then how do we express this? That has been shown here. This is the proportionality constant. Here L is being given as a wear track, and this F has been given as a sliding frequency. Higher and higher sliding frequency, wear rate will increase, and then higher and more wear track length, where it will increase. Now here it is coming a hardness, a lesser and lesser hardness, where it will increase. And another one is the tau, which is showing all integrated time scale, whatever we are mentioning. Again, one more point comes I. Now here I is a transient one. It depends on the time before finally reaching to the steady condition. So whenever we are using the word here I R or I A, they are steady conditions. So that's why the integration really required from a 0 to tau, or maybe say 1 by f, to come up with the results. But major question comes, are these well defined? In literature again there are different relations for this, and we find little difficult to really generalize one. So now coming to the material loss due to corrosion in presence of wear, and that's what we are showing VCC. It can be given as a anodic corrosion current, time of exposure, and this is the atomic weight of the material which is getting deposited, or maybe say getting dissolved in the electrochemical on the electrolyte. Z E is being given as average discharge valency, and F has been given as a constant, which is a constant Faraday constant. D and the rho is the density of the material. T, as I mentioned, the total sliding time. It can be given as sliding distance. But question comes, are these equations generalized? At least we have found literature, we don't find consistent results in this. So there is a difficulty. Now another one, earlier one, which was because of the corrosion. VCC is because of corrosion, and corrosion can be measured by measuring the IAW, and then we are giving also that average discharge valency of the metal. These are the functions. But now coming to the second one, which is a material loss due to wear in presence of corrosion, that's a VWC. That can be given in terms of D, and this area and number of particles. So that has been shown here, number of wear W generation per unit time and per unit apparent area, and then A, and the A is apparent area of contact, V is a sliding velocity, and here instead of time, now here we are writing the total distance. So this is a process. Now one more thing comes, how do we remove the wear debris particle from a surface? So that has been in a few papers, they have explained all complete phenomena from microfatigue mechanism point of view. What's the meaning of that? There will be some crack initiation and then crack propagation, and crack initiation because of the corrosion is easier, and that will get propagated because of the wear. So that's why we say that there is always corrosion assist wear, and then there is a possibility that wear rate will increase significantly. But again, as I mentioned, if top layer, passive layer is there and it is sufficiently hard, it is not getting delaminated, it is preventing further corrosion, it will always be helpful. So in short, if we are understanding this physics or chemistry, then we are able to control or use corrosion in beneficial manner. Now here we are saying this can be a high life cycle or low life cycle fatigue, depending on the situation. One more thing comes, as I mentioned, they are using this as the fracture mechanics or microfatigue mechanism. So that's where the crack propagation has been shown here, crack length, how it will propagate, that has been given expression in this form. So that's why we are saying during sliding wear, a micro crack initiate on the wear surface and propagate at a certain distance after each contact with asperity from a counter surface, ultimately generating wear debris particle after a specific number of contact cycles. And this is what we are saying, low cycle fatigue or high cycle fatigue. Often this number of particle in presence of corrosion will turn out to be a low cycle fatigue. It will not be high cycle fatigue. Particle will get fractured from a surface more easily compared to the without corrosion. So corrosion will help, provided there is a some oxide layer which is not penetratable easily, which remains adhered to the surface, and that will be reducing the wear and reducing the corrosion also. Now this mechanism has been explained from we are again picking up from a literature, and this has been shown here. There is a LED crack, crack tip has been shown in this manner, and then there is a reagent, or maybe say it is acting as a catalyst kind of thing. to enhance the crack. So it is activating this B. That's why, and this B is a bonded, and B star is activated state of B. That has been shown. The crack has been formed in from this point. You can see there is a no connection with other atoms. There is no atom in here, no atom, no atom, no atom, no atom, atom, and slowly this atom also will get a disintegrated. So this, as this get disintegrated slowly, it will move up to this, and this whole chunk will come out, and it will be the wear debris. And that has been shown in this manner. Says the role of corrosion in a wear. Corrosion is discussed as a factor that can accelerate a wear in two ways. Corrosion increases number of potential micro crack initiation sites. That's what I mentioned, that most of the time corrosion is increasing the number of sites, or it really gives initial some sort of reduces toughness, and then creates some crack there. It makes sometime porous also. So number of sites are increasing in presence of the corrosion. Second thing, reactive species which is present in corrosive media, like in this case we are talking about A. So the reactive species present in a corrosion solution will weaken the bond at the crack tip. That has been shown here. This is a tip here now, and promoting the crack propagation and accelerating the wear debris generation. So this is the overall rule, but however we really require a detailed analysis. So here what we are showing, the micro crack propagation mechanism during generation of wear debris particle, and that has been explained. So finally it will come as a wear debris particle. Now, what are the difficulty which we are really facing when we are making a kind of a predictive model? This is major thing is that we don't have a reliable data, and if you when you scan through or read through the literature, most of the data are different, most of the equations are different. So difficulty in obtaining the reliable data for parameter due to the nascent understanding of corrosion, cracking or tribocorrosion phenomena. It's a relatively new topic, and whatever the labs people have done, that remains in that lab, or maybe it is not getting generalized. One of the major issue comes a regeneration and removal of oxide. This is a kind of a dynamic phenomena. There is a regeneration of oxide layer and removal of oxide layer also, and this will be a continuous phenomena, and that's where we are not able to model it everything properly. Now there is some sort of wear map has been shown over here. They are showing here, this is a time scale, or maybe say one of the frequency. If the now frequency is very high, then we are able to see sensitivity on higher side. If load is on a higher side, sensitivity is on a higher side, but hardness is on the higher side, the sensitivity comes down this. So that means the corrosion will reduce. With increase in the load, corrosion will increase. With increase in the frequency, wear will increase. With the increase in the W, wear will increase. With the reducing hardness, corrosion will increase. But here there is a contradiction. Many literature say with a hardness doesn't affect at all corrosion, but in few literatures is shown here. However, every literature say increase in hardness will reduce the wear, but corrosion, there are some sort of contradictory conclusions. We say corrosive wear tend to be dominated by wear induced corrosion at a low load and high interaction frequency, and this is what we show. If the frequency is on the higher side, and while in this case again the load here showing the low, but here it is the load on the higher side. So there are some sort of contradictory thing, and then there are number of relation. Now they divide based on whether the synergy will be medium level, synergy will be high level. So there are some sort of curve fit equation available in literature. You can see here most of the time they are either logarithmic or exponential. High energism also same thing, logarithmic or exponential. So most of the time it is exponential or logarithmic relation, and they keep this constant, and when we do experiments we change it. So it's same thing like in machine learning, we can use a regression analysis, assume some sort of some exponential relation or logarithmic relation. We do number of experiment, we train our ANN model, and then we can find out the results. So this is where we will say that completely data driven model is possible for the tribocorrosion, but that model will remain only for that situation. It will not get generalized, at least in the present time. Maybe in future it can be explored little more in detail, but for presently no. Now another one, there is an empirical relation has been shown, and then I'm showing it from this publication, 1983 publication. They have worked on a synergistic effect of abrasion. So here as I mentioned, we have a 6-7 type of the wear phenomena, but this author have worked on Noel and Ball. They have worked only on abrasion, and then they try to develop some sort of relation. There's a curve fit relation. You can see here they are saying then the wear rate or wear percentage will depend on the load. If increase in the load increases, this wear percentage will come down. So that's why we say empirical relation between corrosion contribution, that's a y, and a normal load. You can see here very clearly this is a negative sign, minus 0.458. Now because of the negative, if the W increases, Y will reduce. So this is very important for us to understand. Now in this case, wear will dominate, but corrosion will not dominate, or corrosion contribution will not be significant. So from same paper we have picked up the from some relations or some figures. You can see here, first is the duration of the corrosion. As the time scale is increasing, corrosion contribution increases. Further, as a load increases, the contribution decreases. Here is a 3, then 1.4, then 1 and zero point 0.9. So these are the low. As we are increasing the load, the contribution of the corrosion is decreasing. Second thing, they have also shown here very clearly that contribution of corrosion also depends on the what was the initial surface roughness. So this is very important. From beginning of the course we are saying the surface important plays very important role, and that also is now coming to tribocorrosion. In this case also, that tribocorrosion surface roughness very plays a very important role. And then they have shown it also depends on the time. Again, there is no linear relation as such, there is exponential relation, and this has been also shown. So there are number of parameters: the temperature, load, surface roughness, hardness of the abrasive material, then kind of the shape of the abrasive material. So there are many relations and many parameters, and we need to develop a relation. So when we do experiments in our lab, we need to choose which parameters are very important. We can do some PCA, we can initially assume 10 variable, and after doing initial experiment we can reduce to 3 to 4, and then we can find out the relevant relation. This so that we can estimate the life of the component also. So this is what the next two slide I'm going to show this purpose. Now here we are saying the purpose of full corrosion. We want corrosion with a purpose. We have something in our mind. So what we did some sort of chemical doping, and then we added a HCl, that's a very low percentage of HCl, to see what is happening to the oil. And we found that oil get degraded, and then degradation of oil can be estimated. That means if I want to predict the 5,000 hours operation, 10,000 operation, that can be done. That means if we understand the corrosion in proper manner, we can really figure out in proper manner also. So this is where we are saying that we added aqueous HCl. And what is aqueous HCl? We use 36.46% of HCl. In this case, what is a conflicting? We say there is a formation of oxide layer because we are trying to reduce the wear and friction, but there is also possibility that because of the HCl corrosion, wear rate will increase. Now why and from where we got this idea? We know very well the EP additives, extreme pressure additives, they try to make a masking layer. They make a layer, very thin layer on a surface, so that excessive load can be prevented. And the same thing is being done by the HCl. We are able to really go ahead with extreme pressure condition. Applied load can be significantly increased, but it also increases the wear rate. So there is a trade-off, and we need to really come up with the right results. For this purpose, we need to monitor water content also, because if overall water content in oil increases by beyond 0.2%, then again there is a problem. In addition, whatever the estimate standard says the 10 value, we need to also check the 10 value should remain well within a limit also. One more thing is coming, that as we seen in previous slide, there is a mostly logarithmic relation between these chemical actions. So here we found a logarithmic relation between pH and aqueous HCl. That means I know how much HCl to be added, to make a pH equal to 1, pH equal to 2, or pH equal to -1 also. This is what has been shown. Now overall the outcome depends on many factors. So what kind of base oil I'm choosing, what kind of HCl concentration, what are the material properties, whether aluminum or stainless steel, or which material I'm using, how many hours I'm operating, and then finally what is the environment there. If there is a change in environment, humidity and temperature, again results will change. So because there are so many variables, that's why the generalization of equation is difficult. Only we have a data driven model remaining, that whatever we do, we try to get a data and try to figure out, and we keep changing or using better algorithms to improve that relation. Of course, as I mentioned, that using this SCL percentage, we could increase the load carrying capacity of the lubricant, but there was a problem that it doesn't work as a anti-wear. It increases the wear rate compared to the without SCL. And what we did in this case, we say that pH turn out to be more sensitive. There's a 10 value, and future we should keep tracking our pH if we want to know what will be the lubricant properties, and if lubricant properties are changing, what will be the properties of the material. So this was done for the gear test setup, and then we found out. Now we have also made a pH sensor, and in future we'll be doing online testing related to pH sensor with a gear test rig. These are the some relation from our publication which are showing here. Initially we got some data. Of course, we use some regression model. If we go ahead with a more number of data, we can go ahead with any ML regression model. In the pH value versus time, here this pH versus HCl, and then here pH value versus time. Again has been shown incorporating the degraded oil of this one is a fresh oil, and this is the degraded oil. And finally we are able to come up with some equation, data driven equation. We say aging time can be calculated by thinking how much HCl should be added, how much aging of the oil will happen because of that, and if we'll be able to predict that, and of course it will be exponential or logarithmic relation, whichever manner you want to express. This is possible, and here we use a very small quantity of the HCl, that's a 0.0025%, which is almost negligible, and that itself creates a aging of oil like 7521 hours. That means we can do accelerated test by learning tribocorrosion phenomena properly, and we can really do accelerated test with a proper judgment. Now this is what we have already done. Now question comes whether we should do it or not. This slide was already shown to you that many times we are talking about to judging the what will be the remaining useful life, basically to find out the prognosis. Question comes, do I really require it? Because we have been mentioning in so many lectures that we should do condition monitoring, we should do condition monitoring, we should get a data, we should go with a data driven approach. But now question comes, do we really require that, or shall we take a judgment? How much is the investment, and what are the output and what are the outcomes? So that's why I say, because of the varied nature of corrosion and wear, as well as the hidden behavior of degradation mechanism, still the mechanisms are not very clear. We don't have any generalized equation. Estimating failure time of system using theoretical created degradation model is a problematic. That's why we really require a machine learning algorithms. And to understand, to develop this, we required the condition based monitoring, modeling, degradation, data driven residual life estimation, and economics. Now this is important. We have been talking all the goody points, but what is the economics? Are we really going to get some advantage from that or not? So that's why we are going to cover a few slides, and maybe I'll be using a very elementary approach. But when you go for the economics, detailed approaches are also available. We'll just touch up what is the approach and how shall we do it, go ahead with that. So now there are a number of approaches. We say we can do a corrosion cost analysis, we can do a life cycle cost analysis, we can do cost benefit analysis also. Again, we really require many experiments to get this kind of results. In industry, they keep a logbook so they can get a number of data, and they keep recording all those data. So they conduct thorough analysis to establish actual cost of the corrosion within an organization. They find out the region where the high corrosion related expenses, so that whenever they find this kind of expenses are high, they can implement. But expenses are not on a higher side, and whatever the sensor cost, monitoring cost, recording cost, if it is going on a higher side, that should not be done. Then maybe condition based monitoring may not be correct. So that's why we are saying focus on implementing cost cutting actions. So if we are going to use a condition based monitoring, and we are not able to get a very good returns, then we may not really require this. Coming to life cycle cost analysis, we say assess overall cost of assets throughout the full life cycle. Not necessarily when I started a sensor and it will remain for the 5 years, 4 years, 3 years. We need to look at also what will be the life of the sensor, life of the component, life of the overall unit. If it is only 1 year and 2 year or 3 year, more chances of the breakdown of those systems. Again, I may not go with the investment. So we can say that consider the long-term corrosion cost in decision making regarding asset selection, operation, and maintenance strategies. So this is very important for us. So we will take one example related to this. Then we say the cost benefit analysis. We need to figure out what is economic viability if we are going to go ahead with the corrosion control techniques. Now here we say weight cost. We need to prevent the corrosion or mitigate the corrosion, but are we able to really see the reduction in the downtime and improve the safety environment? But when we come to the industry, then only we will have a realistic data. In academic world, we can make any case, but in real case, we really require a real data, so that overall cost benefit analysis can be done appropriately. If we have those data, we can say that it's like the most cost effective corrosion management solution. So this is possible. I'll just cover the two very simple examples from mathematics point of view. But when we have a data, we can analyze thoroughly. So let's see first what we say economic analysis of on the controlling surface degradation. We need to think about whether allocate the fund appropriately or not. What are the ways? We say what are the values of the what is the value of the protective measures, cost saving or reduce material degradation minus cost of the protective measures. Now whatever the benefit we are going to get by saving the cost or reduction in material degradation, and what is the equivalent cost for that, and then we need to go ahead with the whatever expenditure, because we are going to purchase some sensor, we are going to hire some person, we want to really keep some sort of hard disk drive, and then continuously monitoring it. So there will be costs of those measures, those protective measures, and what are the really advantages, we need to see that also. So that will give you the value of the protective measures. Now question comes, is it the right equation? No, may not be correct. Reason being protective measure with inclusion by considering the time factor. Here we did not first equation, we are not considering the time factor, which is not correct. So whatever we do, we need to bring everything in the present time. So that's why I say present value of the protective measure, present value of the cost saving or reduced material degradation, present value of cost of the protective measures. Because when we are buying anything, we need to pay money immediately, but benefit will come after 1 year, 2 year, 3 year, 4 year, and there's already depreciation. So we need to account those effects also. For that purpose, I'm just showing in the one example. In this case, that is what we say value minus cost, because most of the time the cost will be negative, and what are the saving, and that this is the annuity, and that's what we are saying based on annual annuity. And now here we are talking about number of years and the rate of returns. Many industries, they want a rate of return of 15%, some industry 10%, there are some new innovation and it can be 5%, or sometime it's a government funded easy loan, then it can be lesser, even 1%, 2%, 3%. So here for time being we are assuming the 10 year as a life, number of years is, and then rate of return 5%, 10%, 15%. So a can be calculated based on this formula. First it will come out to be 7.72, 6.14, and this is a 5.02. So here, as the rate of return expectation increases, we need to show the returns in a lesser year. In this case, we are same return we are showing in 7.72 years, while here in this case we have to show in a 5 years time. So this is very important to take a decision. What is our expectation? And this is what we're showing, the when we plot diagram and we say this is a positive profit and this is a negative losses. Anytime whatever we are taking measure, if comes in a positive, we can take a decision. However, if it enters in this domain, then we should not take a decision. Yeah, maybe in the situation we really require some sort of government supports. So we need to really be very clear that what we want and how we want. And another thing is coming the saving. Often saving is a probabilistic, may not be 100% deterministic. And probabilistic is something like without taking measures, what is the probability of failure? And then with taking preventive measures, what the probability of failure, and what will be the cost of the failure if the component fails, what will happen. So this is a what we calculate the saving. If there's some pipe blast because of corrosion, what will be overall impact, what will be overall cost, we need to consider. Again, as I say, these are the probabilistic. We need to show the probability of failure and probability of success. So here we are saying probability of failure when preventive measures have not been accounted. Here probability of failure where preventive measures have been accounted. So these things are important. Now this has been already shown. Now I'll take one simple example. We say here, assume likelihood of failure in absence of any preventive measure is a zero point 0.3. This is a probability of the failure 0.3. Expenses of each failure occurrence is something like 100,000 INR. That's the cost has been given. If likelihood of the failure drops to the 0.1, this is the probability of failure when we take a preventive measures. So the here says it will be simple, 0.3 minus 0.1 into 100,000, that will overall turn out to be 20,000 INR. So this is a saving. Now this saving need to be multiplied with a ANR, and then whatever the cost, initial cost which we have done with the incurred, that need to be added. Then whatever the value comes, if it is on positive side, we say yeah, we can go ahead. If it is negative side, either we require some sort of support from other agencies or we need to wait so that cost comes down. Right. So we are saying the estimating rate of material degradation is a challenge because there is a little information provided to help decide whether or not take this kind of measures to mitigate the degradation. Investment subject to material degradation might decrease as required rate of return rises. Another one that no, as I showed that if the returns are 15% expectation, naturally we need to say that yeah, we really require a degradation minimization mitigation so that it can really show the longer life. So it is often case of the company wherever that there is a business which has a risky business, more chances of failure. People take a little more risk, or we say the rate of return, and then often we really required a very good knowledge feedback system and we say advanced machine learning algorithms, artificial intelligence to overcome these challenges. Still there's a challenge to take a decision, and particularly we do not have so much knowledge about all parameter, and major thing is that what will be the synergy between those parameters, how one parameter is going to affect other parameter. Those things are important and we need to keep in mind. Now like coming to the life cycle cost analysis, LCCA, which we have already shown, you say in this case we count acquisition cost, operational cost, maintenance cost and disposal cost. So many times the disposal cost is also positive, we need to discard and we need to pay money, and sometimes disposal cost is a negative, that we will be getting money return. So this is very important. Now coming to recurring cost, often recurring cost is known as the operating cost and maintenance cost, that has been shown, and this is a residual cost or disposal cost that can be shown very clearly, LCCA minus AC minus RC. This present value factor what we have learned in previous slide will be same here, because we need to convert everything in the present time. It cannot be after 5 years there is some value, that value we need to convert in the present so that we can compare easily. So let's take example here. Initial cost for something we have to pay around 12,000, and the recurring cost is something 1,000 and 35,500 per year, and final disposal costs are what we are going to get. A residual cost is 3,000, and we say the time frame is a 5 years. So this is the 5 years. Rate of interest is 8%. That was the expectation for us. So 8% here. Now everything need to be changed in the present time. So this is already present to 12,000. Now here 4,500, and then we are going to incur this cost every year. So that's why we really required this formula. That means in the first year, in the whatever we are spending after first year, the factor will turn out to be based on this ratio 0.92593. Second year it will turn out to be 0.85734. Third year it will turn out to be 0.79383. Of course we can do a two decimal convergence rounding off also. So these are the factor, and then if you multiply, it will come out to be something like a 17,967. Now 3,000 will be getting after 5 years, but what is the value today is something like a today value is the 2041. So you sum up. Now here we summing this plus this minus this, because here it is a positive, it will turn out to be a 17,000, it will turn out to be 27,925. This is already we have say recurring cost to present time is this much. This is a LCA. Now this is what to be counted. Now if you go with the benefit one, we need to say how many benefit we are getting and compare it. So this is a life cycle cost analysis. Life cycle cost analysis we can figure out this manner. Of course I'm showing very simple examples, but when we go for complex example, it will be method will be more or less same, but we really require realistic data. And this is what is shown here. The same thing calculation you can do MATLAB, we can do an Excel sheet similar way, and results can be shown. Now last slide in this, you say cost benefit analysis. In this case what we are trying to see, what is the net present value, and what will be the present value of the future benefit, and present value of the future cost. So this is what we require, net present value. And often we say the benefit to the cost ratio, which is of more interest to us, it should be more than 1. If it is a more than 1, then we are ready to invest. So present value of the future benefit, present value of the future cost, this factor will remain similar manner. So here in this case we are showing that initial cost is something like 100,000, benefit in after first year is a 50,000, benefit in second year 30,000, benefit in third year is a 60,000. So overall is a 3 years duration. So we can compare here the initial cost, we need to convert in the present time. This is instead of 50,000 it will turn out to be 47,169. Instead of 30,000 it turning out to be 26,699, and instead of 60,000 it's turning out to be 50,377. Now we need to sum up and then calculate. It turns out to be this PVC is already 100,000, with a benefit we are getting as a 124,000 roughly. So net benefit has been shown as a 24,247. Benefit to the cost ratio is turning out to be 1.2425. So if this is the case, we can take this as a suggestion, a decision, and we can go ahead with the preventive measure to get overall results, and we can implement it. With this, I say thank you for attending this lecture. Thank you.